So today we are discussing about a new chapter which is chemical bonding. So in this chapter we will be discussing about its introduction, under which we will be discussing about orbitals, orbitals and their overlapping of orbitals, and then we discuss about the hybridization. Then the third point that we discuss here is ड्रैगो molecules के बारे में, and then the fourth point is bond angles comparison, and then the determination of hybridization. After that, it will be the introduction part of chemical bonding, the new unit that we are going to start today. So after introduction, we will be discussing about the second part, inside which we will be discussing about the steric number 2 to 8, right, number 2 to 8. After that, we will be discussing about the hybridization in odd electron species. It will come under the third part. In third part, the first is hybridization in odd electron species. Then we are discussing about the Fazan rule. After that, we will discuss about the dipole moment, and then the back bonding, and then the last is the application of back bondings. So, and the last part that we are discussing in this next part is the fourth part, is the part 4. Here we are discussing about the MOTs of some atoms and molecules, MOTs and their graphs and their structures. So these are the main important points that we are discussing further down below in this unit. Now, for going to the main topics, let's discuss some basics about this unit. So what is a chemical bond? So a bond is a force of attraction that holds atoms together to form a molecule. So the question arises, why do we need to do the chemical bonding, or why do the bonds are formed? So individual atoms are high energy. Individual atoms are not stable. So to gain stability, the molecules are formed. Now let's discuss about the important rule that we have studied in our early classes, which is an octet rule. So according to this rule, a molecule in which certain atom's outermost shell has 8 electrons, or we can say that octet rule is the central atom should be surrounded by 8 valence electrons. So some example of octet rule is the molecule which follow octet rule is just like CH4, a carbon and 4 hydrogens are present. So the number of electrons here are 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons are present here. So octet of this carbon and these are complete. So this is a stable species and it has 8 valence electrons. So it follow octet rule. There are some molecules which do not follow octet rule, and those are called hypovalent, hypovalent and hypervalent. There's a difference. These are hypervalent and hypovalent. So these are the two types of molecule. These two types of molecule can be formed, which are just like in hypovalent. If then electron deficient species are present, just like the example of hypovalent molecule is just say BF3. It is example of hypovalent molecule. And example of hypervalent molecule is PCl5, in which more than 10 valence electron are present. And in BF3 molecule 6 valence electron are present. So these are the example of two types of hypovalent and hypervalent molecule. So there are some conditions for which an hypovalent or the 10 electron species can be formed. So to get the hypervalent structure, we need to fulfill some conditions. So first condition, the availability of vacant d orbital. Vacant d orbital must be present. And the next important condition or the species has to be the participation of vacant d orbital must be present, or the side atom should have electronegative group attached with it. So these are the conditions which need to be fulfilled to be an hypervalent species. Some example of these are just like that PH5 is not an hypervalent species, or these do not exist, but PCl5 is exist, and SF6 is also exist, which is a hypervalent species. Well, in second period element, just like in NCl5 is not exist because it do not have d orbital, it only have p orbital. So this do not form hypervalent species. So basically an hypovalent species are those species which have less than 8 electron, and hypervalent species are those species which have more than 8 valence electrons. Now let's get back to our first topic, which is orbitals. What are orbitals? So orbitals are the point where the probability of finding an electron is maximum. So these are the points in which probability of finding an electron is maximum. So there are few orbitals just like S, P, D, and this some delta. These are the orbitals that we see in chemistry. So their properties, and there are some points which can be present which can be studied individually about these orbitals. Let's discuss about that. So these are some special point which is important for s orbital. Let's discuss the first orbital, which is s. So this is the basic structure of s orbital or electron density. This is just like this. So the characteristic of s orbital is it is spherical in size, and it do not have any nodes. What node is? Node is just like the empty part that where probability of finding electron is 0. So these are the parts in lobes in which the probability of finding electron is 0. So these are called nodes. So the s orbital do not have any nodes because of its circular nature, and here center of symmetry or inversion is present, so it is G-red in nature. If the center of symmetry is present, then this is called G-red. And let's talk about the single phase. It is a single phase. What this means is it is not having any phase, just like in the p orbital. It has phases just like positive and negative. So these are two phases were present. So it is not a single phase molecule, single phase orbital. And in s orbital, shielding power of s is maximum, and the penetrating power of s is also maximum, and as does and decreases on afterwards. And it is S orbital are non-directional, means it do not have any direction. And let's talk about the p orbital next. So it is a dumbbell shaped orbitals. It have one nodes. This is a node. And p orbital are directional in nature. So this is directional in nature, means positive charge is here, negative charge is here. So these are directional in nature. Not a single phase are present. So positive, negative, both phases are present. So it is not a single phase, just like S orbital. Center of symmetry is absent, so inversion is absent here because of the positive. If you go here, that is positive, and if you go here, it is negative. So there is no inversion in the orbital. Next is it is ungeared. So if center of symmetry is absent, so it is ungeared. If it is present, then it is geared. So these are the difference in those two. And it has a less shielding power as compared to S orbitals. So these are some important point for S. Now let's talk about the d orbitals, which is an important orbital. So these have non-axial and axial d orbital. Non-axial d orbitals and axial d orbitals. Two types of d orbitals are present. So in non-axial d orbitals, lobes are present in between the axis. Means the lobes, just like if the axis is passing through this, then lobes are present in between the axis. So these are called non-directional d orbitals. And axial d orbitals are those, axial means this is axial d orbitals. So in axial d orbital, the lobes are present in between the axis, on the axis. So these are dx square minus y square and dz square minus y square, dz square minus y square. These two lobes are merged because of their stability. So these two lobes are merged and form a dz square molecule. So the structure of dz square is just like this. It have conical nodes. It has a conical nodes just like this. It has two conical nodes present in this structure. So its basic structure is z along. So this is the structure of z orbital. So now let's discuss about some important property, just like the d orbital is double dumbbell in shape. So it has double dumbbell shape, just like one dumbbell and another dumbbell. So it is called double dumbbell shape. And it is center of symmetry here is present, because if we go from here to here, it is positive, and if we go from here to here, it is positive. Here it is negative, and here it is negative. So the center of symmetry here is present, or inversion which is present here. So it is geared in nature. And there are two nodes are present in this. So one node from here and one node from here. So let's give the name of this orbitals, d orbital. So there are pure d orbitals and impure d orbitals. So in pure d orbitals, the name of these are dxy, dyz, dzx, and dx square minus y square. And when a dz square is come, so it is called an impure d orbital. So there the properties of these are, it has four lobes and it has two planar nodes, and they can form delta bonds. So by combination of these, delta bond can be formed. This is the next type of bonds. And if we talk about the impure d orbital or dz square, two lobes are present and one ring are present. So as we have seen in the back, this is the structure of dz square. So these are the structure. So here they cannot form delta bond. So dz square do not form delta bond. It has two canonical nodes. So as we have seen, it has two canonical nodes. So these are the two nodes, one from here and one from another direction. So here another concept is that these are the formation of bonds, how the bonds are formed. So as we have studied in our previous lectures, a head-to-head overlapping forms a sigma bond. So a head-to-head overlapping form a sigma bond, and a sidewise overlapping, just like this, form a pi bond, and a face-wise overlapping form a delta bond. What's a face-wise overlapping? Means these faces are connected with another molecule's faces. So is this connected with this, and this connected with this with this, and this with this. These are called overlapping bonds. So here in phase wise overlapping, 4 overlapping bonds are present, and in pi bond 2 overlapping zones are present, and in sigma bond 1 overlapping zone are present. Now let's discuss about the very important topic, which is hybridization. What is hybridization? So it is a mixing of atomic orbital of different energies to form a hybrid orbital of equal energies. So what is the need of hybridization? So the first is that as we have studied in previous slide, that the s orbital is non-directional, or it do not have any directional nature. So and p orbital is directional in nature. So as we have seen the structure of p orbital, it is just like dumbbell shape, so double dumbbell shape. And if we put an s orbital in between, so due to this repulsion between the s, or the size of this s orbital, repulsion between the central atom, so the central atom will repel each other, and this so molecule is not sterically stable. So this molecule is not sterically stable, and unhybrid orbitals are formed. So after mixing with s orbital, what happened is that it makes an hybrid orbital. So these are the example of hybrid orbital, these are the example of unhybrid orbitals. So what happened in hybrid orbital is that the bond angle between this carbon is increased. So this bond angle is greater than 90 degree, and here no repulsion between the side atoms. So these side atoms which are attached do not repel each other. So these are the hybrid orbitals in which one lobe is greater size and another is small, and one lobe is greater size and another is small, and this will be the angle. And here the molecules are sterically stable in hybrid orbitals. So as we have seen that the sp molecule or sp2 molecule or sp3 molecule, the bond angle is 180 degree for sp, and here the s character is maximum because of one s and one p orbital. So the contribution per atom contribution here is 50-50. So 180 degree angle is there here, and in sp2 the 120 angle is there because the contribution of s here is a little less, and in 33.3 something, and this here it is 50%, and here it is 25% or 25% s and 75% p character, and here the bond angle will be 109 degree. So as we have studied, if the percent s character increases of the molecule, if the percent s character increases of the molecule, then it is directly proportional to the bond angle. If percent s character increases, the bond angle also increases. So if we go from left to right, the bond angle increases. So there is a question arises, can a molecule form without hybridization? Then the answer is yes, and those type of molecules which form without hybridization are called Drago molecules. So there are some conditions to fulfill for what is the Drago molecule. So first condition that is very essential for the formation of Drago molecule is that central atom should be larger and from third period or onwards. So it cannot be from second period, it must be from the third period and onwards to be able to form a Drago molecule. And the second condition is central atom should be small and have less electronegative character. So the second is that, and the third one is that the central atom should have less lone pair. Central atom should have lone pair, but the lone pair must be present in the central atom. And what happened here is that this is the normal structure, and these are the small size of side atom. So they do not repel each other. So no repulsion between the side atom because of the small size. So no need of hybridization. So hybridization की जरूरत नहीं पड़ती है. And these molecules are called Drago molecules. So these are the condition of Drago molecules. And some examples of Drago molecule are as PH3, ASH3, SBH3, BiH3, and HS2, SEH2, and TeH2, and POH2. These are all the examples of Drago molecule where no hybridization is possible and the bond angle is 90 degree here because of this 90-degree bond angle, and these bonds formed are weak because these bonds are formed by unhybrid orbitals. So these are called unhybrid orbitals. As we have seen, these are unhybrid orbitals. So the formation of bonds from unhybrid orbital is weaker as compared to hybrid orbitals.